To understand the impacts of indoor air pollution on the people inside a room or building, we need to know the concentration of the pollutants in that space and how they change with time and activity. We can do this by making a mathematical model of the room that includes the pollutant emissions, losses to surfaces and reactions, ventilation with the outdoors, and any other strategies that are used to reduce pollutant amounts. One such very common and very useful model is what's known as box model. In a box model, we pretend that the room or building is one big box, and we account for all the sources of a pollutant and all the things that can happen to it in the room and estimate what the concentration would be. A key assumption in a box model is that the air in the box, aka the room, is well mixed. By well mixed, we mean that the concentration of the pollutant is the same everywhere in the room. It does not matter if the pollutant source is in one corner. We assume that the air currents rapidly mix the pollutant throughout the room. In most rooms, the well-mixed assumption is reasonable. Think about how quickly the smell of a plug-in air freshener fills up a room. Mixing is faster when there's movement in a room, for example, when people are moving around or if there's a fan going. While the well-mixed assumption is usually reasonable, we should always keep in mind that it's not perfect, and you can find local hot spots near sources where the concentration of the pollutant is somewhat higher than everywhere else. For example, respiratory virus concentrations are likely to be higher very close to a contagious person. But let's go through some examples with the well-mixed assumption in mind. Imagine we have a completely sealed room, no airflow in and out, and no pollution at first. Now imagine a constant source of a pollutant is turned on, like someone starts cleaning with chemicals or lights a scented candle. If the pollutant is not sticky and does not chemically react, for example CO2, then the concentration in the air will just keep going up and up and up and up and up. Not good, right? This is the reason that ventilation is so important. Ventilation helps to keep pollutant concentrations from accumulating to high levels by removing the dirty air from inside a room and bringing in cleaner air. When we turn on a little bit of ventilation, at first things look the same. The pollution starts building up inside the room. But as time passes, the line representing the amount of the pollutant starts to curve towards lower values. This is because even though the pollutant is still being emitted by the source, some of it is also being flushed out of the air by ventilation. The more we increase ventilation, the more the concentration will drop. However, this assumes we're ventilating with clean outside air. If the outside air has some of the pollutant in it, then the indoor concentration will not go down as much with ventilation. And if the outside air has a higher concentration of the pollutant than the indoor air, the ventilation will actually increase the indoor concentration even more. In most cases, pollutant concentrations are lower outdoors, and therefore we want to make sure we have enough ventilation to help bring down the indoor pollutant concentrations. In a previous module, we also discussed other ways that pollutants can get out of the air. Namely, pollutants can stick to surfaces in the room, undergo chemical reactions, or be actively removed, such as with a filter. All these processes help lower the amount of the pollutant in the air, similar to how ventilation does. The main difference is just how much they help bring that concentration curve down over time. Usually our most effective methods for removal are more active ones, like ventilation and filtration. So far in our box model scenario, we said that the pollutant source was turned on and continuously releasing pollutants. But what happens if the amount released changes over time? For example, because the number of people in a room changes, or because the activity happens only now and then. As the source changes, the pollutant concentration will go up and down in response to the change in the amount being released. More pollution being released in the room means the concentration in the indoor air will increase, and if we decrease the amount being released into the room, we'll likewise see the concentration in the indoor air begin to decrease as well. Because it takes time for things to even out, there's always a delay in how the indoor air concentration changes from any change in the source. Overall, we can use box models to understand how the concentrations of pollutants indoors depend on various factors. Ultimately, this helps us to visualize the two main ways we can reduce indoor air pollutant concentrations: reduce the source of emissions or increase the removal from the air.